Right. Thanks, Simon. I recently joined Facebook Reality Labs. That's why that logo is there. But this work is from my time at University of Waterloo in collaboration with Cheng and Dan Vogel from Waterloo and Hui-Shyong and Quigley from University of St. Andrews. So let's get started. I'm going to talk about a text entry technique that we designed for augmented reality called RotoSwype. So what do we want from a text entry technique for augmented reality glasses? What are the desired attributes for text entry in augmented reality, specifically for the glasses? We know that interactions in AR need to support on-the-go use, situations where the user is mobile or on the go. And therefore, in our opinion, at the very least, it needs to satisfy these criteria. The first one is that the technique should be unencumbered. That is, I don't want to encumber my hands with a controller like we do for VR. I don't want to lug around a controller everywhere I go and then take it out and then finally get to use it. Secondly, it should be eyes on glass, which essentially means that I want to stay focused on the glasses and not necessarily have to look at my hands that are performing the interaction. Thirdly, it should at least be single-handed. Right? In a lot of on-the-go situations, we are holding things in our hands, like shopping bags, briefcases, wallets. And so you want at least one of your hands to be completely free. And finally, QWERTY. It will be nice to not move away from the familiarity of QWERTY, which, as we have seen, is very resilient to anything us researchers might have to say about it. So basically, you can only use one hand. You cannot hold a controller in that hand. You cannot see your hand, all the while typing on a QWERTY keyboard, right? And of course, we want it to be as fast and accurate and as less physically and mentally demanding as possible. So that's the problem that we are tackling. And there are some very interesting existing techniques out there that try to do this. The first one on the left is typing on a watch for AR, which requires the second hand to a certain extent and reported a speed of 10 words per minute in the last session of their multi-session study. The second one is typing on the touch surface of the glasses themselves, and this reported a speed of 8.7 words per minute in the last session. The third one is also typing on glass, but it uses gestures with word prediction instead of QWERTY and gives about 9.7 words per minute. And finally, for reference, typing with a controller in the hand reportedly gives us about 15 words per minute. And so one of the goals for us was to make a technique that can offer a better performance to the user while adhering to the desired attributes that we have established. And therefore, we proposed RotoSwype, a technique that uses a ring on the index finger along with word gesture typing, which is a popular mechanism for text input on our smartphones, where we draw word gestures on the touchscreen. Right? And you can see that on the slide. So the ring here is a simple IMU, inertial motion unit, along with a clickable button that you can see on the side. So the way this works is that the wrist rotation is captured by the ring and converted into a gesture trace for the keyboard XY plane. And we use a direct mapping of the wrist rotation to the XY plane. So when the user holds their hand in this position that you see on the extreme left, that corresponds to the center of the keyboard plane, right? And then the vertical wrist rotation, which is essentially the pitch rotation axis, is mapped to the y-axis of the keyboard. And the horizontal rotation, which is the roll rotation axis, is mapped to the x-axis of the keyboard. Now, as you can see, we prescribe the pitch rotation range that maps to the keyboard to be 70 degrees and the roll rotation range to be 100 degrees. And the goal here was to maximize the range of wrist rotation so it can enable enough precision on the keyboard. But at the same time, it should be comfortable for a majority of users. And therefore, we took into account the ergonomic ranges that are reported in the literature for wrist rotation. and also conducted a pilot study to arrive at these final figures, the angles that you see. We also considered other wrist rotation mappings. So for example, on the right, you can see that the palm is facing the ground instead of facing the side, and this leads to a different mapping. It's still pitch and roll, but the wrist movements are now different. And we did a study to find out which mapping works best. And our original mapping on the left performed significantly better. I'll refer you to the paper for more details on this. Now let's take a look at our apparatus that simulates gesture typing, the gesture decoding on a headset. Our goal was to see how RotoSwype would perform with a state-of-the-art word gesture decoding algorithm. And the only state-of-the-art word gesture decoding algorithms right now are on smartphones. And therefore, we simulated touch gestures on an Android phone's SwiftKey keyboard that supports word gesture decoding. We placed this phone inside this Mogo headset, which is a commercial headset that allows the user to see the phone screen clearly, even when it is so close to the eyes. And you can see the user wearing this headset and wearing the ring in that third picture. So to type out a word, the user clicks the button on the ring to start simulating the touches, and then clicks again when they need to stop. Right. So this is a simple setup. It does not exactly replicate AR glasses 100%, but it's a very useful and low fidelity way of utilizing an existing word gesture typing decoder on a headset. So let's see the working system in action. On the left is what the user sees inside the headset. The user presses the button and rotates their wrist to generate the gesture trace on the keyboard. And you can see how subtle this motion is, but still very, very accurate. And now the user can also go to one of those suggestions that you see on the top and select them using the ring. Now, one thing that you'll notice in this picture is that the user is sitting and their elbow is resting on the table, right? But if the user is doing this motion in air without any support, then the arm will get fatigued pretty quickly, something that's called the gorilla arm effect. And this problem is, of course, present in other techniques as well, like typing on glasses or using a controller, because your hands are always in air. And therefore, we designed a version of RotoSwype that overcomes this gorilla arm issue by supporting a relaxed hand down pose. So this is how the user does it in the hand down pose. Notice how relaxed and subtle this interaction is compared to what we do with controllers in VR or even with the touch on the glasses. It's a difference of night and day in terms of fatigue. And because you're only using a thumb and a finger, you can imagine that we can do this while we are holding small things even in the same hand. So for example, I can hold things like cards, keys, or coins in my 3 remaining fingers while doing this typing. Right, so the question now is, how well does this work? And so we conducted a 5-day evaluation to see the performance of both hand up and hand down postures. We had a between subjects design with 16 participants, each participant transcribing 20 phrases each day for 5 continuous days. And here are the results for speed. The y-axis shows the mean speed in words per minute, and the x-axis shows the days from 1 to 5. So the speed was about 9 words per minute on day 1, and by the 5th day, the users were able to type with almost 15 words per minute. The effect of days on speed was statistically significant. The 2 postures, as you can see, have very similar speeds. Another thing to notice here is that there are no signs of the performance plateauing. And that means that 15 words per minute is definitely not the ceiling of how fast RotoSwype can go eventually. And in fact, we asked 4 participants to do 2 more days of the study, and by the 7th day, they were able to reach speeds of 17 to 22 words per minute. And they were still improving. And if you think about it, these speeds are not bad for a simple low-power IMU-based ring. Here are the error rates. So the graph shows the error rate percentage over the 5 days, which is a standard metric that essentially is the percentage of words that the participants got incorrect in the final transcribed phrase. So the error rate was about 3% on day 1, and it reduced to 0.5 to 1% by day 5. We also asked participants to rate the mental and physical demand on a 7-point Likert scale after day 1 and after day 5. And you can see that on day 1, both of them are pretty high. And this is actually because it takes participants a bit of time to get used to performing the wrist rotation according to the mapping that's required. But by day 5, both the mental and physical demand come down as participants get more comfortable. And in fact, some participants also hinted at muscle memory coming into play. So for example, one user said, when I see the word the, I just type it automatically. I don't have to think or look at the keyboard. And this means that with long-term use, participants may start developing a nice muscle memory for more and more words and improve the performance even further. And so if we take a look back at the reported final session speeds for the existing techniques, RotoSwype seems to perform better, coming close to the performance with a handheld controller. But of course, this is only an informal meta-comparison between existing investigations and not a formal comparative study. So overall, RotoSwype achieves high performance while adhering to the 4 desired attributes that we set out to achieve. At the same time, RotoSwype also supports relaxed use, and it can be used for text input not just for AR, but for other devices as well. For example, distant screens or televisions or any other device that you can think of. Now, I just want to draw your attention towards something interesting in the 2 postures that we investigated. On the left, you have the hand up posture, and on the right, you have the hand down. And this is that the hand down posture has a different wrist rotation corresponding to the x-axis of the keyboard. Right? It's only 70 degrees compared to 100 degrees there. So the ranges are pretty different. And this is the x-axis of the keyboard where you have 10 buttons, so you need a lot of precision, right? But as you saw in the results, the performance of hand down and hand up are very similar, both in terms of speed and accuracy. So what is happening here? These results basically tell us that, one, the users are able to be precise enough even in the smaller range. And second, that the word gesture decoding algorithm is tolerant to a certain amount of deviation. And these 2 observations open up some very interesting future directions of research. One is, how much can we reduce the wrist rotation range while maintaining the same accuracy? Because reducing the range will mean that the wrist has to travel less distance and therefore be even faster. The second potential direction is that given that the word gesture typing decoder does not require a very high level of precision, what other modalities can we apply this form of indirect gesture typing to? Right? And you can let your imagination run wild over what those modalities can be. And finally, of course, a major challenge is to integrate high-performance typing for out-of-vocabulary words, numbers, and symbols into the ring so that it can be used together with word gesture typing. And with that, I'll end. Thank you. Open for questions.
Thank you very much, Aakar. So we think we have some questions over here.
Hi, Raimund Dachselt, Interactive Media Lab Dresden. This is really excellent work and a great idea. And I was wondering a little bit about the mapping to a planar keyboard. So the swipe keyboard is a planar keyboard, it's a plane, whereas your gestures are performed in 3D space. So did you think about mapping this to a rather curved version of the swipe keyboard, which is somehow more appropriate to the spatial gestures you do?
Okay, you mean curved in the 2D sort of space or curved in the 3D space? Actually.
Yeah, that you basically like the swipe keyboard would be a texture on a curved object, 3D object, like, and you map it. Your spatial rotation, you map it to a curved swipe keyboard. Yeah,
that's actually a very neat idea. Yeah, I frankly, I mean, I haven't really given a thought to it, but it may turn out that the performance improves because
it could improve. Perhaps.
You're right. Yeah. Thanks for that suggestion. Thank you.
Hi, Aakar. Nice talk. Aman Parnami from IIIT Delhi. I was just wondering if you observed any confusion that the participants had related to change in the mapping that one could have because of one of the conditions that you tested was hand up in the air and the other one was pointing downwards. And so could you reflect a little bit on that?
So these were between subjects studies, both of them. So one participant only did one technique, not two techniques, so they did not face any confusion.
Did you otherwise find any difficulty level change for the participant in the mapping in both the conditions, even if the participant did not go through both of the conditions?
Yeah, so there are, the reason why, let me actually go to that. So these are the two conditions, palm to the side and palm to the ground. And the reason why palm to the ground performs worse than palm to the side is, so there are multiple reasons, but mostly ergonomic, is because when your hand is to the side, then you have equal rotational range in both directions, whereas when it is here, then you don't have equal rotational range in both directions. That's one reason. The other reason that the users told us was that it's a bit unintuitive just doing sort of palm to ground because, I don't know, I mean, the exact sort of, because I keep playing around with it, so for me it's very intuitive, but they said that it's very unintuitive to do this. Maybe, again, because of the asymmetry.
May I?
Yes.
Jai, Google. Just a simple clarification is that, did you do a coordinate transformation, or is one degrees freedom map to X and the other degree freedom matches to Y in your mapping? Or did you do some coordinate transformation?
So essentially what we are doing is that it's an XY. It's not, so it's a 2D space. Essentially what we have is a 2D polar coordinate and then a 2D XY plane. And so we did mapping from that particular point to that particular point. So yeah, it's a coordinate transformation in a way. You can.
So it is a transformation rather than just one-to-one.
Yeah, it's not a one-to-one because ultimately the user has to also go to the corners of the keyboard, right? It's not just this or this. The user has to go to the corners of the keyboard and span the whole area. And so it's yeah.
And how much the learning is? You said in terms of days. How much time do they do per day?
So they did 20 phrases per day, which essentially meant that initially they were, it took them about 15 to 20 minutes. By the fifth day, it took them anywhere from 7 to 10 minutes. Yeah.
So on day one, so every day your performance report is the average of the 20 phrases, or is the last phrase? In other words, how intuitive
it's the average. It's the average.
So how intuitive is it in the very beginning, like the very?
In the initial. So let me actually.
Or it's more feedback driven in the beginning.
What's that?
You might need to image.
Okay.
So actually there's a Kai town hall happening now, so you guys may want to take that on offline, please. I would like to thank our speakers one last time. So yes, thank you very much.